Negative binomial distributions are a special case of binomial distributions. Um, in the case that we're still looking at the trials being independent, each trial outcome being classified as success or a failure, the probability of the success is the same for each trial, but the difference for a negative binomial distribution is that the last trial must be a success. So what we're really looking at with a negative binomial distribution is that we're looking at how many observations will give us that kth success, or however many number of successes that we're looking for on that very last trial. And so when we compare regular binomial versus negative binomial, in the binomial case, we have a fixed number of trials that we're looking at. But in negative binomial, we're looking at how many trials it takes to get a specific number of successes. And so when we look at the formula for the negative binomial distribution, we're looking at that probability density function. Here would be the number of attempts in, R would be our number of successes, and P is once again the probability of success. So here we still hit the probability of success raised to the number of successes, the probability of failure raised to the number of failures, but our combination formula is a little bit different. And so if we further convert this probability density function, it actually simplifies to looking at that combination that we looked at before. And it may not look simple, but it is very quite simple when we start doing it in Excel, especially when you are applying that negative binomial distribution on it. So one of the significant properties here is that the expected variance is going to be greater than the mean for the expected value for your x. So that makes this distribution a very attractive property when our data are over dispersed, and when the variance is higher than our expected value. So that would be one of the situations in which we would use a negative binomial application. And so here we have an example where you just input your variables into the formula, and we're trying to use the probability of success as 0.7 to determine the probability that it will take 5 tries to get 3 successes. So, you know, this is what I will look like when you try to compute that probability. In this case, it would be 0.185. And so here's just another example using different values of n and what those probabilities would be for various levels of n. So when we look at the graph of different negative binomial distributions, this is what that graph would look like when we have different values for p as well as different variables for r.